want to recover, phosphorus together with organics for animal feeding process, then this is a very effective process to recover both for the as animal feeding by product for cow and other economical animals for the large scale food process plants. Next slide, please. Yeah, so I just introduced the general concept of the phosphorus recovery, and then I want to provide two case studies. One is technology I haven't had the opportunity to work on directly, which is the phosphorus removal and recovery from the liquid phase. And also there is another case study about phosphorus removal and recovery from the digested sludge, which is the technology I worked on directly from the lab scale to the full scale installation. For the phosphorus removal and recovery from liquid phase, there are several companies have been very successful and have installed multiple installations in US and also in other parts of the world. For example, the Ostera nutrient recovery technology is one of the leading companies in this industry to recover phosphorus from the liquid phase. They have done a very good job to improve the recovery ratio by carefully design the recycle ratio of the reactor and by controlling the struvite fines that is caused by too much super saturation of the struvite crystallization condition. So in addition to Ostera, there are two additional companies that has full-scale installation in US, including Multiform Harvest and Nourisis. The Multiform Harvest is now a subsidiary of Ostera at this time. Next slide, please. So this is a public information, and this is a patent application in the USPTO, and this shows the general process about the liquid phase phosphorus recovery through a struvite reactor. Essentially, it is very important to control the right concentration of ammonia, the right concentration of phosphate, and the proper concentration of magnesium. In addition to that, there is a critical step to recycle the effluent of the struvite reactor back to a certain point of the crystallization reactor, so that the escaped struvite fines can be captured and granulized onto the larger crystals that has been seeded directly into the reactor. So this is a granulation process that takes a fairly long time to form a very massively looking struvite granulate. Next slide, please. Here is the schematic from the Ostera process brochure, which is also publicly available online. And this shows it shows the general location of the process. This process is located after anaerobic digestion. It receives the liquid phase from thickening process and from the dewatering process, and it treats the supernatant or the dewatering centrate or filtrate directly, and it can form a struvite granulate and be dried and bagged into a commercially available fertilizer. They do have a commercially available fertilizer brand called Crystal Green that you can buy from Amazon website. If you are interested in the product, you can have a try and see how well it will work for your plants. Next slide, please. As we have talked about the liquid phase recovery, I want to provide additional information about phosphorus removal and recovery from digested sludge. This is a process that is different from the liquid phase recovery. However, it shares the same chemical reaction principle, and it can recover a substantial amount of phosphorus as true white in the digested sludge without extensive extensive renovation of the plumbing at a given treatment plant. So two companies right now are doing phosphorus recovery from digested sludge, including Synthesis and CMP, and also a Belgian company, a Belgian technology called Neurisis. The two technologies actually share the same principle. They just happen to be branded by different companies. So I'm going to use the product I worked on with Synthesis CMP as an example, but the principle should be very similar between the two technologies. Next slide, please. So based on the name, the phosphorus removal and recovery from digested sludge happens after anaerobic digestion. Most likely, it is a methanogenic digester, and it could be installed after acid-phase digester or aerobic digester, but additional chemicals will be supplied for the process. This is an installation that is in operation since 2018 in Howard County, Maryland, not far away from from DC. This is the second digested sludge recovery process installed in the U.S. and it has been worked well. Although we encountered some operational issues that have been addressed and learned a lot from the first several installations. But in general, this process is installed after anaerobic digestion, but before dewatering process. Next slide, please. Here are several photos to show the development process for the phosphorus removal and recovery from digested sludge. First of all, this technology has been tried and installed in Europe since 2009, but hasn't been installed until 2017 in US. So this is the first technology to recover the phosphorus from digested sludge in US, installed in the municipal wastewater treatment process. I was lucky, I was lucky to be a student. Next slide, please. I was lucky to be a student with Professor Stenstrom because I never thought I'm gonna to work with aeration with the digested sludge, because most of the time the aeration technology is for the aerobic treatment process. But aeration is actually a fundamentally important process or engineering approach to do a lot of things, including wastewater treatment and in this case phosphorus removal and recovery from the digested sludge. The difference between aeration studies for the wastewater treatment and the aeration trial for digested sludge is we are looking at different gases. For the aeration in the wastewater, most of the focus is on the oxygen transfer rate. For the phosphorus recovery from the digested sludge, we are focusing on the stripping of carbon dioxide. However, most of the gas transfer coefficients are based on oxygen. There's very limited information about carbon dioxide gas transfer information in the digested sludge. So by looking at my previous study notes from the classes and also work with the engineers in the company, we developed kind of a approach to estimate the gas transfer efficiency for carbon dioxide stripping by aerating the digested sludge. Essentially, we assume the performance of oxygen transfer will be equal to carbon dioxide because the two gases are close to ideal gas, and supposedly the ideal gas should perform the same under normal conditions. So this is kind of the fundamental principle. We estimated the gas transfer efficiency for carbon dioxide in the digested sludge by aerate the sludge and monitor the oxygen concentration. Next slide, please. Here is some more detailed information. I have screwed some of the data shown here, so it is not the authentic data for the design. However, it is the data to show the trend of the gas transfer efficiency and also the KLA value for the gas transfer in the digested sludge, which is a very different matrix in comparison with mixed liquor in the aeration basin. We have fairly low gas transfer coefficiency. However, we supply a lot of air into the sludge so that we are able to strip the carbon dioxide fairly quickly in the digested sludge. Next slide, please. So here shows some of the design values of the aeration air diffusers for different installations. Again, those values are skewed, so it is not the authentic design data, but to show the trend. Essentially, we do both theoretical calculation and field studies to compare what we calculated and what we get from the pilot test. On the left-hand side, this is some of the field conditions we obtained from the full-scale installations, both in Europe and in US. On the right-hand side, it is a figure to show how we control the aeration intensity by applying aeration at a different level of the reactor. The air to sludge ratio is fairly high, and it could be energy intensive if the reactor is not designed in the right geometry. This is all still a very active area. We try to optimize the reactor design to minimize the energy consumption due to aeration. However, considering the volume of the side stream in a wastewater treatment process, this wouldn't be a huge problem. Although it's always good to optimize the efficiency, but typically the side stream, especially the flow of the digested sludge, is only 1 to 2% of the wastewater flow in a typical wastewater treatment plant. So even though we aerate the sludge at a very high air to sludge ratio, the overall energy consumption might be still lower than try to do than try to control the phosphorus in the mainstream, which is a wastewater stream. Next slide, please.
John, you have just a couple minutes left.
Okay, I'll speed up. Yeah, here is just an example to show that as an environmental engineer, it may be beneficial to also get exposure to different disciplines, especially have the opportunity to have the access to the knowledge in a very good university. In this case, I learned a lot about the electrical engineering and also the system control principles that is tremendously helpful once you try to address a real world problem. Next slide, please. Here is a kind of a general summary about the phosphorus removal and recovery from the digested sludge. There are certain kind of general treatment performance guarantees we can provide as a technology provider. And also there are some downsides of the phosphorus removal and recovery from the digested sludge, including increase of phosphorus content in the dewatered biosolids. It may not be an issue in many states, but it could be an issue in certain agriculture states, including Wisconsin, Iowa, where they have a regulation to limit how much phosphorus in the biosolids that you can apply on the land. So it could be a concern or a topic to look into in the design phase of the technology selection. Next slide, please. Besides the phosphorus recovery from the digested sludge, there are additional benefits to recover phosphorus, including improve the dewaterability of the biosolids. Before going to the dewatering process, I won't run into the details, but there are a very good research conducted by the Virginia Tech University that they look into the mechanism of why recover phosphorus from the digested sludge can improve the dewaterability of biosolids. Another good university is Bucknell University, that they also developed a very good experimental procedures to determine how much the dewaterability can be improved. Additional benefits of removal side stream phosphorus is to reduce the phosphorus loading on the mainstream. This slide is provided by Blair Wisdom, who is an engineer in the Denver Metro water reclamation plant. Basically, they are looking at the impact of the phosphorus recovery technology on the secondary effluent soluble P. As you can see here, no matter you recover phosphorus from the liquid phase or digested sludge, it will be beneficial to the plant operation in regards to reduce the effluent P concentration. Next slide, please. As a quick note here, the recovery of true white in digested sludge directly is a feasible technology. The metal content is in compliance with the biosolids regulation, and the true white purity is fairly good. Most of the time, we can achieve at least 85% of the purity, with additional impurities as sands or organics. I believe that's my last of my slides. Thank you.
So, brief summary, you can see that nitrogen and phosphorus, they're important eutrophication factors for sensitive water bodies. So that's why we're motivated to remove them, in addition to preventing nitrogen accumulation in reclaimed waters. And so the processes we've shown you here are in the order of 20 to 30% removal of the mass that comes in, perhaps more if your main process is removing nitrogen and phosphorus. And we haven't shown the footprints exactly, but John mentioned 1 to 2% flow of the digested sludges. And when you calculate retention times and so forth, you discover that the footprint is pretty small. And hopefully this can be done on the existing property. The chemical processes for removal of wastewater, but it results in lots of sludge. But when we do BioP, we hopefully have less of that, and we make a fertilizer that's actually valuable and can be sold. And you know, these plants that we're talking about now have multiple options for removing and so forth. And so the last comment is where all the mine phosphorus goes. And one of the things that motivated me to provide this seminar was futurists are saying we're going to run out of phosphorus before we run out of oil. And so this recovery is important. So we're at 2:03 now. I'm still here. If there's any questions, John and Henryk and I'll be glad to answer them.
Thanks to all the speakers. It was very interesting. I think we're just a little bit over time. Some students had other classes starting at 2. Even I'm on a different Zoom call on my phone, but I was listening up until. So thank you again. But yes, any questions or comments from those who are able to stay a couple of minutes longer?
So Henryk, your office looks like you're a professor. All those books behind you.
I have a quick questions on, because I saw one comments that there are lots of nutrients in the Santa Monica Bay, and it has created some issues with. Can you tell a little bit more about that? I didn't know much about this.
Well, I said that, and that goes back to when Keith Stolzenbach was still with us, because he was more involved with ocean processes than most of the rest of us, and he was doing mass balances with a couple of other faculty members who were beginning to suspect that the red tides that are observed in Santa Monica Bay, which usually aren't visible to just bystanders, but the fish know it, and they're suggesting that it's a nitrogen limited phenomena that could be controlled by nitrogen limitations. Generally, phosphorus is rate limiting in freshwater bodies and nitrogen in ocean bodies, but it's a concern. And one of my motivations was to see if the big plants might do some phosphorus removal with side stream, and that way they might postpone any expansions that might require phosphorus or nitrogen removal in the mainstreams. So I don't have a paper for you, but there's a faculty member over at the IOES, Rebecca, that wrote some stuff on this.
So is this because of Hyperion plants that are releasing wastewater, or is something different?
Well, it's Hyperion. There's a lot of nitrogen in the urban runoff, not as much phosphorus. But the joint plant, it doesn't discharge into Santa Monica Bay, but it discharges into off of White's Point, which is connected to the ocean waters when you look at the recirculations and so forth. So there are some modeling there's some modeling done by folks in the Atmospheric Sciences Department on some of this distribution, and I think they have more recent information than I have on that.
Yeah, it's a interesting problem. DOE just released a plan for the nutrient recovery that Eric just forwarded to all of us.
Right, I saw that.
It's a problem that we have to solve. It's just so much benefit in multiple different ways.
Well, this would be sort of at the opposite boundary condition for needs, because this would have a very small footprint compared to the footprint of the other plant. Henryk has worked with some of those full-scale installations, and he's reported some. Well, do you have anything to say about the greenhouse method that we heard a few weeks ago?
The clear ass process, you mean?
Yes.
Yeah, clearly it works exceedingly well, but the practicality of implementing it at large scale is pretty daunting. In Salt Lake City, they built a fairly major demonstration facility that the state paid for, about $20 million worth of investment that they made in it. And I think it only processes it's less than 1 million gallons a day. And the problem is that you need so much glass. And at that time, this is going back about 18 months, there's only one company in the world, in Germany, that could make that type of glass. And so they were beholden to them. And they were obviously being gouged in terms of their relative cost of selling the glass to them. The other thing is, I don't know if they showed you pictures of these long tubes of algae, but the problem is that you have to put in these U-shaped pieces at each end of the glass so as to connect up the reactor. And so that's a point of failure, especially in places that have earthquake risk, because the slightest amount of tremor is going to cause the whole house of cards to come down. And that's problematic. The one in Salt Lake City is actually not worked very well. And the theory is that something is inhibiting the growth of the algae. So it's been a bit of an expensive demonstration plant, but there are smaller plants up in Montana, in the Midwest, that have worked very well at the sort of 200,000 gallon a day scale. It's translating that into something that is reliable and inexpensive compared to what we can do today with, say, using concrete. It's a heck of a challenge. The technology works, there's no two ways about it, but there are significant physical challenges to making it work.
Okay, well, it's getting late, so I guess we ought to sign off. But Professor Mahindra will post this, and the three of us will welcome any questions from you. You can send us emails.
Thank you.
Absolutely. Thank you again for, Henryk and John. It was a pleasure. And yes, I will record this. I will upload it to our box folder so the faculty and students have access to that. And our department administrator can put them on a private YouTube channel. So we can even send you a link to that. It's not publicly on YouTube, but with a specific link, you'd be able to view it.
Okay.
Thank you again.
Thank you. It's my pleasure.
Okay.
All right. Bye-bye.